Good morning, everyone. Today I will deliver the lecture titled Foundational Models for Medical Text. This will be part of your course on AI Foundation Models in Biomedicine. And I'm happy that every one of you have joined and please feel free to let me know if you have any questions at the end. So some facts about me is that I recently graduated with a PhD in computer science from IIT Kharagpur, India, and I particularly specialize in natural language processing and AI for medicine. Currently, I am pursuing a postdoc at the Stanford Medicine. Given this background, let me go directly into the talk. We will first cover some background on the foundational models, like what are the recent advances, what are the industry trends, why it is so successful, and then we'll go into some fundamental concepts like causal language modeling, how you train it, and then we'll shift to the focus on like foundational models for the medical text domain. How do you train? What are the different architectures that we have seen, and what is working, what is not working? And at the end, we'll go to the evaluation, right? So this is content is based most of is based on my previous years talk in the same course and also my tutorial that I delivered at Wisdom 2025. Based on the last year, what I have added new topics that was not present in the above two places are some industry use cases, AI agents, reasoning models, and the MedHelp evaluation. What we don't cover is the fairness, bias mitigation, neurosymbolic approaches, clinical and health informatics aspects of it when you try the interoperability issues that we face when we try to go from the model development to the deployment stage. Finally, there is no programming content that is covered here. We don't cover any non-text modalities like vision, sensors, or multimodality, right? Uh, I hope those will be covered in different other lectures of your course. So let's continue. So first, as you know, that LLMs have a huge potential to transform healthcare, and the clinical text processing techniques are gaining traction in clinical workflows and deploy it because LLMs are known to hallucinate. The paradigm that we are now kind of agreed upon is to target low risk, high potential use cases uh, that can be like more on the administrative burden aspect or the first draft access rather than expert systems where you have to like the LLMs are doing the diagnosis, right? So specifically, we see the following places like it can help to reduce the burnout and the cognitive burden in the medical professionals. Secondly, it is a very good tool for patient engagement because they have a good capability on intent recognition, also customizing the content to the different user needs that are there. So it has found to be very good in the pediatric medicine component where instead of just so in order to get more empathetic messages as well as engage with the patients for a longer duration to better understand um, the recommendations. It also has shown to improve overdose and suicide prediction based on EE charts and also like in triaging in the emergency departments. So what is unique about the foundational models or what is the main paradigm that had shifted? So prior to this, there would be like for each individual task, there will be each individual models, which was usually trained using a specific labeled amount of data. So what it led is basically two, three issues. First is you need good amount of fine-tuning data for each of these tasks. Um, Second, you need um, you need to store these different models and they are not able to learn from the labeled data from the other tasks. Third, these in specifically in healthcare, the demographics are so different across the world that a global standard is not possible. So There has been like a very huge covariance shift when you use models trained on one demographic to other, and usually the performance was very poor. Um, so this was the first big paradigm shift where we have this one foundational models which is not trained on like specific task, but it is trained at following instructions. So it is pre-trained on a huge corpus of data. So it knows usually for the purpose we one is to predict the next words, which will go in detail, and secondly, some feedback from the humans. But essentially, a huge corpus is trained, and instead of individual task or fine-tuning on individual task, it is trained well to follow instructions. So the idea is, suppose if I want a summarization model, I will ask tell it to just summarize and give specific instructions, and it will be able to do the summarization task instead of using specific fine-tuned or very large amounts of labeled example. That was the previous paradigm. And if you see, the most recent one is open evidence. That is a tool that is so you have really a lot of open source LLMs, right? But open evidence is a very recent tool that has been targeted for clinicians. And you can see this, it prioritizes very like good knowledge sources, like it can be the clinical guidelines, the NEJM, that is the journals, and yeah, so it is targeted fully for them. And this is the interface of how it looks. It is currently made freely available for all the clinicians, and let's see where it goes. So given this particular prompt, it gives a much more detailed answer, as you will see in case in comparison to other open source, not open source, other closed source models or even open source models. And the important fact is it also gives very detailed references. So people can just understand what these references are, and so that if they're not satisfied, they can go into more detail. Mm. Um, Then there is a huge influx in terms of the generative AI for healthcare startups. Um, you can see that there are different verticals where where there has been like a lot of startups growing up. So I'll quickly cover over some of them. Is first is patient engagement. The idea is these foundation models, LLMs, allow uh, conversing in natural languages. Um, so it can basically target, say, pre-consultation stage where they are trying to look for doctors. They have a specific issue and they don't know which providers to go to. Um, so this removes the search friction that they go through, and this helps basically in this pre-consultation stage and also the booking stage where there is much more less friction that they have. Then also in the documentation stage, you can think in this manner that these transcribes, like the medical scribes, like they were people who used to do this inscription one during the conversation as well as from for the billing and also the coding parts to identify from the text as well as the lab reports, which is the ideal coding. So there is a big amount of money that was spent, and but also a huge amount of coding errors also occurred, and that led to many issues. That led to higher turnaround time when one's try to get uh, insurance companies to pay for certain treatments. Then in care decision making, this can help in terms of, say, like getting through this huge corpus of recent information, like which are the most applicable drugs, which drugs have some known side effects in interacting with other drugs. Um, so this is kind of getting one updated with all the existing knowledge and uh, taking the decision whether this additional knowledge is important for the current decision making. So mainly getting evidence-based care and getting up to date. Then from the prior auth part, this is when doctor or when a doctor or a provider wants to give a treatment or a drug, it has, in some cases, it has to ask for prior authorizations from the insurance. And yeah, so many startups have built to make this part more easier so that there are less coding errors. There are you can follow up more. It is not just submission of the claims, but also following up in case there are, or also appealing if the claims are denied, right? Coding parts, these are like once you have this discharge note, if you want to save it in the AHR, you have to code it in some you have to code it in the following certain standards, and LLMs helps reduce those coding errors, right? So given this overview and what are the use case or the startups around it, so in terms of if you go to specifically to NLP, what we can see are it can help in summarize the visits. um, it can help in generating letters, referral letters. It can be either for insurance, or it can be like if you are going to someone for a second opinion, or you're continuing the care at a different place, so some handoff notes for continuity. The LLMs are very good at instruction data extraction. So given any unstructured data or any modality, it is able to extract the data with very less hallucinations in that way. So given this industry use cases, so let us slowly go into what are the issues with the commercialized LLMs, right? So out of the box, you can see you can directly access Gemini, you can access OpenAI GPT-5 models. But what are the issues with it? First, um, when you are working with medical data, there are two aspects. One is the PHI data, that which contains personal health information. So it has serious restrictions on it. Like you cannot use it with these like with this out of the box platforms. You need to have these on an organizational level, these business associate agreement under HIPAA Act, in if you want to use PHI data in your prompts. So it is not directly available in these free plans that you have. Or for individuals, some of the premium plans offer this privacy or localized, like the data stays local, right? Right. So given these limitations, at least, but with non-PHI data, I think you can go out with it normally, and that's why you have seen a lot of work around non-PHI data like clinical guidelines or paper or biomedical articles in that way, right? So to understand um, the LLMs, we have to, so we are spending good amount of time understanding where it is deployed. Like for that, you also have these regulations. So before going to model development, I wanted to give you an overview of the deployment scenario. Because in AI in healthcare, that is the big difference. It is not just about model development. It is also about how do you develop the model, how does it get adopted into practice. And in those cases, when you think on adoption, these regulations come into play. So the most prominent ones in US is the HIPAA Act, that is the Health Insurance Portability and Accountability Act. And it protects, its main aim is to protect patients' privacy and take informed consent of patients when you use their data. Specifically, when we talk about this personal health, protected health information, these are the 18 attributes that are covered by it. And yeah, so you need to, so if you use PHI data, you go through more stricter regulations. So that's why there are de-identification methods that, given some discharge notes, um, they remove by certain de-identification measures these 18 attributes, which include like name, phone number, then email IDs, IP addresses, then SSN IDs, um, as much as unique like demographic details. You can tell the state, but you cannot go to the zip code level in that way, right? And if you use PHI, you have to sign a business associate agreement with the LLM provider, which basically ensures that you do not train the model on the PHI data. You have a much stronger encryption, and you maintain the logs in case of audits in that way. Um, yeah, I think we have covered this. Then now more recently we have the AI Act from EU, where they basically had some exemptions for of AI for military national security research purposes or for non-professional use. So basically, it puts stricter restrictions on and duties on AI providers and on organizations that use AI in a professional context, right? Um, then also then num some non-exist AI applications by and they have this risk-based categorization, so that is new here. So the first takeaway point is that um, these limitations are on the AI providers and organizations that use AI in office. So it does not apply to research purposes, national security, military. Second, it has a risk-based approach. So in terms of the level of risks which they have defined, the restrictions are more stricter and stricter. Also, there's an AI Act. The exact implementations will be deliberated and given out by the AI office maybe in mid of 2026. So in terms of the risk-based categorization is that application with unacceptable risks are banned. High-risk applications where in which AI systems for health fall under, they must comply with the security, transparency, and quality obligations and undergo conformity assessments. Um, Limited risk applications have only transparency obligations and minimal risk are not regulated. So they have this risk-based approach in the regulations that are enforced. So one important aspect that you have seen is the transparency aspect. It means that you have to inform the users, or when you're audited, you must be told that um, there is like what the data provenance, what is the risk-based approach that you have taken, and what are the limitations or capability of the system, and if you think it will affect human behavior in some way, you have to tell them about their rights. And currently it is a little bit vague in setting, but the main theme is that it should make the humans aware that first they are communicating with an AI systems. If there are some assumptions that may affect it, it should be communicated. So that is transparency in the response. Documentation is the backend thing, and data provenance is a traceability aspect is how this response generated, that what are the sources that was used to um, come up with this response, and again in terms of model training, what assumptions were made, what parameters were used for model training, which pre-training data was used. Um, Now we slowly move on. Once we are kind of aware on the deployment aspect, the regulations, and the real life scenarios, let us slowly move into the model development phase. As you can see that these closed source models have over the years have done very good on benchmarks, but not just like in medical, you cannot just show performance on the benchmarks. You have to also show results on the other axes like consensus, like the safety or the risks, like what is the likelihood of harm, what is the extent of harm, what are the demographic biases it exists. So it is not just accuracy, but also other axes that you have to also evaluate on. So some will briefly go to the fundamentals, as I think it is already covered in your previous lectures. So basically it is a causal language modeling, that is it is when it is trained, because it is trained on huge corpus of data. That is why these language models are so big, 32 billion parameters or much larger. Um, in terms of weights, but in terms of the pre-training corpus, it is in trillions of tokens. It is trained on that. And the basic way is that you are given a part of the sentence and you are told to predict the next word. And this repeats on and on. Um, so it is unidirectional context. Instead of self-attention, you have masked self-attention, right? And it is good for generative tasks because it is unidirectional in nature, right? Um, And if you think more deeply, that the next token prediction task is basically a multi-class classification task where you have to predict um, which of the tokens in your vocabulary is next, right? So if your vocabulary size is denoted by V, so it is, you have to decide one token out of this entire vocabulary size, right? And so you basically have a distribution that you do, a probability distribution that you predict, that, that you give some probability on some words, and that is compared against the correct word or the correct token that was there. So the vector it is compared against is a binary vector that is all zeros except the right word that is kept one, and you compute this cross entropy loss, and this is how um, you generate the loss, and you try to minimize the loss over multiple iterations, right? So this is the foundations of how these models are trained. Now we'll slowly shift from foundation models to foundational models for the medical domain, right? Why it is required? First is because the traditional approach of fine tuning works better if the domain on which it was pre-trained, because it's a large corpus on which it was pre-trained, is similar to the domain on which it is fine-tuned, or the downstream tasks. For example, it is usually done in the open domain like Wikipedia, World Wide Web, Common Crawl. So if your downstream tasks are also on the news or the open domain, it should work well, right? Because it has similar distributions. But when you go to the medical domain, it does not work well because the data distributions are different. Like if you take news articles versus scientific research articles, they have a very different data distribution. In our own works, we have seen that it has a very high vocabulary mismatch, right? That is, medical words are tokenized. When it is tokenized, they split. They have a very higher fragment score. That is, they split into more number of search words on average as compared to an open domain word, and this leads to loss of performance. Um, uh, Fourth, it is very high annotation costs. So if you want to generate label data in the medical domain, you need medical professionals or someone with a medical background, which in turn results in a much higher annotation costs. Finally, you have to also show results with in terms of you have to also evaluate in terms of clinical utility. So you cannot just show benchmark results on a benchmark. You have to also show it led the summaries led to gave more relevance. They were less repetitive. So it basically has a clinical utility which is evaluated by the clinicians, right? And the most simpler approach, as was done in the previous domains, was some just fine tuning, and it was found that this is not enough when the shift is so large, right? So the typical ways of how people try to improve the performance in the medical domain is to incorporate high quality domain specific information. So it can be from medical textbooks, it can be clinical practice guidelines, it can be EHR notes, clinical notes, discharge notes. It can be PubMed biomedical literature. And the idea is if we can incorporate that in the training stage, um, or in the verification or evaluation stage, we can slowly improve the LLM performance. So given that idea, there has been a surge of like LLMs that have been developed. Some are developed, as you can see, um, usually in the 7 billion, 13 billion parameter size. They usually, their backbone is an open source model, like in this case. So I think this is from 2024, this survey. So they have this Llama 2 backbones. Recently it will be Llama 3.1. Um, and then they will be trained. Either they can be continually pre-trained, which you can see in case of Meditron and PMC Llama, or it can be just instruction tuned. Most of them are trained on biomedical literature because it is easily available. One of the main reason clinical notes, slowly there had been de-identified clinical notes that have come out, mimic is one of the biggest sources, but it is not as much as the PubMed literature, right? So we can see a combination of both continual pre-training as well as just simple instruction tuning approaches that have been worked. So as you can see, if you introduce continual pre-training, it will uh, lead to usage of much higher training compute, but it will lead to a much more better trained model. So in the initial stages, people just use instruction tuning, and the idea is um, that just by following instruction, it can uh, understand, like just by seeing few examples, it can understand what is the task at hand, right? So now, given this background, we have in the first half we went through the um, AI fundamentals, why AI healthcare is needed, the current trends, how it has been used in industry, the regulation aspects, and what is considered during deployment. Now we'll focus on the model development side and let us see how much we can cover, right? So I will try to spend more time on the newer advancements like the AI agents and the large reasoning models, and also we have vocabulary adaptation, which is much more recent, and less time on the older variations, right? Um, so if you want to see an overview, this is what we have till now. So in context learning and prompting, this is very well known. This is just prompting. So you take an LLM model which has a chat, which is a chat model because it has to now follow instructions. If you take a chat version of the model and you tell it that, okay, Roger has 5 tennis balls, and the answer may be sometimes be wrong. But it has been found that one is if you give examples to it instead of just telling it to give what is that instead of describing the task just like by some sentences, give an example of it. So if it is one, it is called one shot. If it is zero, it is called zero shot. And if it's more than that, it is called few shot. So this is also known as the in context learning. So the idea is to give a better task description. The second advancement came was that instead of just telling it to tell the answer, if you tell it to think, that is, think step by step. This is the very famous chain of thought prompting, and the idea is that this somewhat like for some reason triggers LLM to think, break down into multiple reasoning steps, and usually this leads to the right answer, right? Then there was this self-consistency prompting. The idea is instead of just giving out one answer, because you have to remember when it is generating an output, there is a randomness associated with it. That is, if you give the same prompt over 10 times, it will give 10 different answers. And this is controlled using the temperature parameter. So to allow diversity in the reasoning aspects, um, the idea is they put a like a higher temperature value, say zero point 0.7 or zero point 0.8, and then the ask the LLMs to give the answer, say 10 times. And the idea is this will lead to more diverse reasoning paths. And if I take the majority voting out of it, then we will get the right answer. So if the majority of the times it will give the right answer, right? Okay. So this Microsoft paper took it to the extreme of prompting. So they said that you don't need fine tuning, but the prompting, if you have multiple sets or multiple variations in prompting and you combine them together, prompting is enough. And they showed this um, in the medicine perspective, right? So the first change is that in the previous settings of few shot, uh, these few shot examples were fixed because the idea is that these few shot examples are just task descriptions, right? So, so if the task stays the same, this did not change. But this paper said that if these examples are more closer or more similar to these to the query in hand, then the performance improves. So this introduced the concept of dynamic few shot, where they used this OpenAI embedding model to embed the query as well as the few short examples, and they take, say, top the key nearest neighbor. If you do this embedding similarity based on cosine similarity, right? And so for each test exam, for each query, uh, the examples in their context is different, and it is closer to what the query is, and this shown to improve the performance. So zero shot to random few shot to random few shot chain of thought, then you have KNN few shot and chain of thought, right? And finally, they observed that this is exactly in the scenario of multiple choice questions, where they saw that if you change the position of the answer like A, B, C, D, so if you shuffle the answers, shuffle the position of these options, then it forces the LLM to again reconsider. And if you do this and again then perform the self-consistency aspect, that is, you change the position of the options and then you ask the LLM to again predict, and this you do over key iterations and you take the majority voting, right? So the idea again is to improve the diversity of the reasoning paths, right? And finally, they were asked to train these self-generated chain of thought. So the chain of thought aspect they also improved, and they like which chain of thought is correct. If the answer is, if the rational is assumed to be correct, if the final answer matches the ground truth answer. So so this is how they could have this self-generated chain of thought, right, for the training purpose. So this will not be possible during test time. And one clear difference is that these GPT-4 rationals were seen to be much longer as compared to those rationals that were developed by the experts. Instruction tuning, this we had briefly just covered before. So in more detail, it is when you want to train the model to follow instructions, right? So you're not training it to do well on particular task. You're training it that if I give you a particular detailed instruction, you follow it end to end. So you start with BERT or T5 pre-trained LLM models, and you fine tune. This was the previous paradigm, right? That you fine tune on task A and you do the inference on task A. Then comes prompting. So you have a pre-trained LLM, you just tell, okay, these are the few short examples, and you tell him to do the task, right? But instruction tuning is that you give it multiple templates where you tell them how to do different tasks. So let us see an example. So these are the input, like instruction tuning examples, and you give, say, 200k such examples, and you then fine tune on it, right? So for example, here is a goal: get a cool sleep on summer days. How would you accomplish this goal? These are the options. And the target is keep stack of pillowcases in the fridge, right? So this is like common sense reasoning. Then for translation, you are given translate this sentence to Spanish. The new office building was built. It is in English, and the answer is in Spanish. So if you give this input and target pairs, and for each input and target pair represents a particular task. This is translation. The left one is reasoning. Then we have sentiment task. And the idea is in future, if you give them an unseen task, for example, the unseen task here is the natural language inference, then the idea is it will be able to follow your instructions and choose one of the three options, that yes is not possible to tell or no, right? And this instruction tuning, when the initial models were starting to come up, because the medical annotations are very difficult. um, this was how PALM model, that is Pathways LLM model, was initially, which was initially PALM, was converted to MedPalm. How? By following this instruction prompt tuning approach, where these were called exemplars. These exemplars and instructions were written by clinical experts themselves. And so the first aspect is kind of the persona, that you are a helpful medical assistant and provide useful company. And they also gave an example that this is the persona and this is the question and how you should answer. And initially, since this were written directly by these experts, so it was in very few numbers. Maximum it will be hundreds. don't exactly remember the number. It will be in hundreds, not more than that, right? And this was used to do this instruction prompt tuning, and that is how they created the MedPalm model. Okay. Some more details about continuous pre-training is that if you have a base model and then you again retrain on a new amount of data, you have to be careful in the sense of what are the parameters, training parameters that you use. Do you use the same learning rate, same batch size, or do you do something different? Because it has been seen that when you do continual pre-training, there is a phenomenon of catastrophic forgetting where you do poor performance on the previous task. So basically, it is not learning something new; it is replacing the new with some of the old tasks, right? So this is has to be stopped, right? So there was this some work on effective continual pre-training, where you use a proportion of the replay data set, where you to not just use the new data set, but say 10%, like in Meditron, they use around 10% of replay data set, uh, which they used along with the new data set, and then they did the training. And this they showed help to reduce catastrophic forgetting, right? But again, this is a you have to try different percentages and see how it works, right? So we have seen for Meditron that they had done it, right? Now, some details about the Meditron pre-training data. So they use clinical guidelines. So it's like 46K. This is something that I'm currently working on. So if you see Wikidoc is not directly a guideline. It is a crowdsource source of data and may not be considered as guidelines. But anyway, it is a good source of information. It may not fall under the category of guidelines. Um, then we have paper abstracts like 16.1 million biomedical literature papers. Then we have full text articles, some are just the abstracts, whereas the PubMed open access subset is the one which has the full text. And finally, we have the replay dataset that was done to uh, prevent catastrophic forgetting. This is usually like they have said 1% of the entire corpus, right? Fine tuning. So this is very a common terminology that we have seen, but um, now when you're aligning LLMs with the medical domain, so this the previous was applied for usually for small language models, right? Because even if the size is small, it is still compute extensive. Now, when you have to align LLMs to the medical domain, it is necessary to adapt and align to the original model with the domain specific data, right? End-to-end fine-tuning is very challenging. And one more important point is that you do not have the similar quantity of medical data as you have the open domain data, right? So in regular fine-tuning, all the model parameter weights gets updated, right? So you have input X pre-trained weights, and this is the final embedding. And when you do this weight update via backpropagation, you update all the weights, right? But full fine tuning is not possible, right? Because of these 13 billion or 7 billion parameter models, it's possible for small language models, right? Secondly, it is seen that in context learning is not very useful for difficult tasks or small language models because this instruction following is seen as an emergent property that is seen in larger models, that is models which are like 70 billion parameter models or above. So in those cases, it is seen to work well. Um, so what do you do for these small models? So the idea is called low rank adaptation or LODA, or some others called this parameter efficient fine tuning. So the idea is basically if you think of these weight update, it can be considered as a matrix updation operation now, or a matrix multiplication operation. But if we reduce the matrix to a lower rank and perform the operations there, in on the lower rank size, so the number of metric multiplications significantly reduces. Um, but what it so the advantage is that the computation cost reduces, right? So this is the main idea, is that now instead of the pre-trained weights, you have add certain weights, because if you just update the weights that you had before, that information may get lost and the transformer may stop working. So the idea is uh, add these layers called as the adapter layers, which are these low rank matrices. And during fine tuning, you just learn the weights of these adapter matrices, right? And you don't touch the pre-trained weights, which stays as it is. To a more Now we are slowly going into more specialized domains of vocabulary adaptation, where the idea is um, that in cases where um, your output contains a large amount of vocabulary words, these methods fail because you are still restricted to the open domain vocabulary till now, right? And it has been seen that these medical words are not tokenized very well, right? So to start, let us go over to the vocabulary basics. Is that each LLM, one is we have a big parameter size, the 13 billion, 7 billion parameters. It also has a model vocabulary. Usually, like for BERT, it was like around 31, 32K, but the recent models of Llama are going towards 128K, and other bigger models are taking much bigger vocabulary sizes. And the idea is each vocabulary has comes with its own embedding, which it learns during its pre-training stage. And when it faces a new word, for example, like erythromycin, right? So it breaks it down into, and if it given to Bird, Bart, and Pegasus, each of them has their own tokenizers. And this is how it is broken down. You can see into like erythromycin is broken down into these five sub words or tokens, right? And this is known as, if you term is known as the fertility or the fragment score. That is the average number of tokens over the entire corpus and for a given vocabulary that the tokenizer splits a word into, right? And it has been seen that this splitting of medical words into more subwords than normal, than average, or leads to one at the encoder's side a poorer representation, because for these words even the average embedding is usually taken for all purposes. On the decoder side, it is much more difficult to generate these medical words, as you have to have these tokens generated in this right order. So main takeaway is that we need to update for these cases where there's high OV concentration or high novelty. We need to update the vocabulary with one from the target vocabulary, right? So this works best on data points like high OV concentration and long form generation. We have checked it for summarization tasks, and we have seen that it works for both the small as well as the large language models. So the standard setup till that time, till now, was for the small language models, that is say BERT, BART, Pegasus. You have this open domain PLM, that is that you come with, and then for a particular task you do uh, here in this case, because it is task specific tuning, you do intermediate fine tuning. That is, you have the CNN Daily Mail dataset, which is a usually made up of this news articles where the headline is where you have the content as the text as the source document, and the headline or the topic, the news article title as the target, right? And in this setup, you have this huge corpus available, and so basically you are training this open domain PLM for the task of summarization. And once it is trained on the task of summarization, you have the medical summarization task, which And this data sets, because it is medical, it is much smaller. That is 700 to 2000 data points is the range. And you train it on this smaller target data set, and so that it works best for the medical domain. So this was a standard setup which was quite successful till that point of time. And the idea is that we wanted to propose is that uh, because we are targeting high vocabulary mismatch cases, we want to update the original vocabulary that has come with, that is the VPLM, with that of the target domain. That is the exact target task, that is the medical summarization task in our case, as well as with VPAC, that is the intermediate training set. So if you see previously here, there was CNN Daily Mail. This we are also replacing with a biomedical dataset, right, which is called as biomedical article title generation. Okay, so we'll not go into much detail on this topic, but the main idea is that um, we are adding some extra vocabulary based on some combination of the target dataset and the intermediate fine-tuning dataset, that is a biomedical dataset. And because we are adding these vocabulary words need to be trained, right? So these words are initialized randomly in some cases, or there are some recent works that have taken um, their tokenization from the source data set and given an average out of it. So it is there in my in the vocabulary adaptation tutorial that I had shared, that I had delivered. If you want to know about it more detail, you can go there. So the idea is that this was possible in case of, and this was then trained, right? This was possible in case of not possible in case of small language models, because if you want to optimize, so this is basically an hyperparameter search. So if you want to do an hyperparameter search, what is your objective? So the objective here would be the fine-tuning performance, right? That if the summarization performance improves, I will keep that. But this is huge. Like if this intermediate fine-tuning data set is around 300K, and in case of here also it is around 200K, so it is a huge data set. So if you want to train, if each for each hyperparameter grid search, you have to train for such a large amount of examples, it is not feasible. So in our work at which was published at ICHKAI, we showed that um, you can approximate that fine-tuned performance by the fertility score. That is, if you see that the fertility score, because when you add more and more words, uh, which are usually medical words, the fertility score will go down, but your vocabulary size will increase. So you have to come up with a trade-off. But instead of optimizing the final fine-tuning performance, which requires training on this intermediate fine-tuning step, if you just optimize the fragment score, which is basically an unsupervised metric which does not require any training. It just requires the current vocabulary size that you have and the corpus you have, and it takes a fraction of the time. And we saw that if we approximate that, we are able to optimize, get an optimal value of the added vocabulary, right? And once we got an optimal vocabulary, we then did a full fine tuning using the intermediate fine tuning data set, and then it showed significant improvements in the medical summarization task. We then continued that work and continued the work in case of large language models, where we saw that where we now cannot perform the full fine tuning. So we showed that if we perform continual pre-training first, which we said that we require when there are significant changes in the task distribution or the task description, where just um, in context learning or just vocabulary, just fine tuning, or just PEFT or low rank adaptation will not work. You need continual pre-training. So here we saw that instead of just LoDA fine tuning, if we do intermediate fine tuning, but here the intermediate fine tuning, which we are called as continual pre-training, because here we do not have a summary to the corpus on which we are pretending is not the summary corpus. Here we show that in the intermediate fine tuning step, if we do just with 20K, because your large language models are quite big enough already, so they have a huge parametric knowledge which was previously missing for small language models, and that was the reason we had to do this huge amount of intermediate fine tuning. uh, so now we can just use a smaller continual pre-training on a smaller number of documents, I don't know, 20K documents. And then if we, so that if on that, if we perform the parameter efficient fine tuning, that is LoRa using adapted layers, we are able to get good performance, right? And in in here we have to update the embedding matrix, because when you're adding this new vocabulary, you have to, the embedding matrix changes, and also you have to update in the unembedding matrix layer, and so the corresponding language modeling head also gets updated. So till now we focused on AI models which are non-compound in nature, or the monolithic AI models. So now we'll slowly go towards compound AI models. So the one which may be more interesting, or the more recent ones, are, first is RAG, that is retrieval augmented generation. So here the simple change is that everything around now is about context engineering. So from prompt engineering, we are moving towards context engineering. That is how good context we can give, right? So here, that's why given the query, because if you see the monolithic LLM, the main issue is that there was an issue of this knowledge cutoff, because these were trained for a till say May 2025, right? And after that, they went through some testing, and then it was finally released in October 2025. But the knowledge cutoff is still as May 2025. So it will not have access to the recent information. So one is that is the recency of the news are missing. So it's not present in the parametric knowledge of the LLMs. And second, if I want to customize these LLMs to my local data store, instead of relying more on the parametric knowledge of the LLMs, um, how to do that? So if you give a local data store, and the retriever is basically a search, so you retrieve from this local store, and that context is customized to your query. So use the query to search your corpus, that your local store or whatever, and then you retrieve that, you add that relevant context in the context of the large language model. So that is basically RAG. So the idea is very simple. And it has been seen that there are, like, you can try different variations of it. So you can try different corpora. Like in medical, you have PubMed, StatPulse is for like point of care. Then we have medical textbooks, Wikipedia, MedCorp. You can try with different corpora. That is from which it will be retrieved, or it can be a combination of that. Then if you think of the retrievers, there can be BM20 is a semantics or syntax based retriever. Then you can have Contrivert, Spectre, MedCPT. Then you can try different LLM versions. And people were trying, and it was showing good performance improvement as compared to the chain of thought prompting. But recent works have shown that because one big reason RAG came into picture is that they wanted to reduce hallucinations by putting the relevant context in the proximity of the context, in the sense that instead of relying on the parametric knowledge of the LLM, they said if I have the relevant answer or the right answer, if I retrieve the right answer or the right paragraph and put it in the context of the LLM, it should surely take that, and the hallucination problem is solved, as it is now grounded to the retrieval corpus, right? But recent works showed that it is not always the case. That even if the correct answer is in the corpus, there is still a conflict between the parametric knowledge of the LLM as well as a retrieved document, as well as within the different retrieved documents that we have. And this conflicts can still give rise to hallucinations. So it is not true that if we use RAG, there will be no hallucinations. If the answer is in the context, it may not be so. And this ICLR paper uh, beautifully demonstrates, gives a much detailed representation of why it is. So, so the main takeaway point is that this parametric knowledge is stored in the fully connected layers, whereas this external context um, is can be understood as if I just copy and paste from the external context, because the external context has this right answer. They said the hallucinations, so the main takeaway from their paper is that the hallucinations occurred when the knowledge FFNs override the parametric knowledge into the residual stream, whereas the copying heads, that is the ones which are responsible for extracting the right context from the external context or the retriever, they lose the information. Retriever or LLM loses the information attended to by the copying heads during the generation process. So during the generation process, there is a struggle between the copying heads and that of the knowledge fully connected layers. Finally, large reasoning models. So this is again a new thing that over the last 1 year it had developed. So I had taken the reason or the definitions that was covered in this particular blog by Sebastian Rasker. It's very beautifully. You can go over to the blog, get more details. So the idea is that you have gone through chain of thought prompting, right? So it can be thought as some kind of prompting, right? But there is a difference that the reasoning, we can call reasoning as a definition. If you think it can be the process where you want to answer, where in order to answer a particular question you have to go through multiple steps, and which is complex in nature, and you have to break it down in small number of steps. It is not like you're explaining the answer, but to generate that answer you need to do step by step or go through multiple steps. So this is what they are defining, is that reasoning as the process of answering questions that require complex multi-step generation with intermediate steps shown like the now intermediate steps can be shown directly in the answer, that is in the response generated by the LLM, or it can be done in the backend and you just get finally the answer to you, right? And how it can be done. So if you think what is reasoning, so if you think, so the question can be what is the capital of India. So if I say it is New Delhi, it is just a fact, right? There is no reasoning directly involved, it is just retrieval of some facts. But if you have these math arithmetic problem, that if a train is moving at 60 miles per hour and travels for 3 hours, how far does it go? So this involves um, multiple steps, right? So if you do not use a reasoning model, it will just say the train travels 180 miles, right? But if you give it to the reasoning model, to the response, and the response, in the response it has the intermediate steps written. So these intermediate steps are known as reasoning traces formally, right? So it will look something like this. To determine the distance traveled, use the formula distance equals to speed into time. Given that the speed is 60 miles per hour and the time is 30 hours, the distance equals to 60 miles per hour into 3 hours is 180 miles, right? So this is because it requires multiple steps which are not simple in nature. Um, that's why this is called as fall under the reasoning category, right? Now the question comes, how to improve the reasoning in LLMs, right? So there are various approaches that people have done till now. First, or the simplest, is the inference time scaling. So inference time scaling is that you do not require any additional costs, but there are higher inference costs. So you don't, it is not that you are like training separately, but maybe you are breaking during inference, you are just breaking your answer into multiple steps. So you are saying that, okay, to answer this task, I have to break it down into 3, 4 tasks. And then you are generating for each of these 3, 4 tasks separately. And then you are finally combining the final answer. Or it can mean that you have multiple models and you are combining the answer. You can have a reasoning model and that you're now combining the answer to give the final answer. So what this will incur is that you do not need any specific training. These models can be just used as the normal LLM that is being used. But since you are running multiple inferences and each inferences gives like required certain tokens, output tokens, it will incur some costs. So in inference time scaling, which people they suggest that maybe the OpenAI O1 model is using such inference time scaling because of its higher inference risk costs per number of tokens. It can be happening, right? The second approach is the pure reinforcement learning framework. This has been shown in case by DeepSeek R1 that was released last year in Jan 2025, and they have a very detailed technical report. It has MIT license, which means it can be reused for commercial use again. So it is less restrictive than the Llama models, right? And here it require much less amount of costs, um, right? Next, the third setup that is considered to work very well is reinforcement learning plus supervised fine-tuning setups. And instead of just a pure reinforcement learning setup, which may take much longer times to converge. Finally, we have distillation setups where if you have like if you see DeepSeek, so you have DeepSeek R1, 32 billion, 8 billion. These are models are all distillation models from the original much larger model, right? So distillation is shown to like significantly improve the reasoning capabilities of these smaller models, right? Um, and But the limitation here is that you have to have a much bigger model and you have to generate large amounts of examples in order to train. So this training so distillation step of training these smaller models is also compute intensive, but it works well. So that is the take. Um, So these are very recent work that I'm trying to share with you so that you get to know the cutting edge is that these reasoning traces. So there is a lot of works on safety or alignment that it should follow the instructions that we are seeing. Um, so we have seen a lot of improvements there. So in their main response, um, there is very good alignment or they're following the instructions. But the reasoning traces, the recent work found that for these open source large reasoning model like GPT, OSS, Quen 3, and DeepSeek R1, they less than 25% of the reasoning traces adhere to the instructions that was given. And they also suggested some ways to improve it, like using multi-turn reasoning and reasoning instruction fine tuning using synthetic data. So if you're interested, these are very recent works. You can go through it. Um, Also, um, in terms of reasoning traces, and in medical applications, there is this very recent work that was published in EMLP where they used where the first as a reasoning model does, it generates reasoning steps, step one, step two. But the point to note here is that all these reasoning steps traces are generated in a zero shot fashion. That is, the LLMs are just asked and they create from their mental model these reasoning traces. So there is no guidance or control over them. So in this paper, they wanted to understand whether these reasoning traces are factually correct or not. So for each reasoning trace that it generated, it used an LLM. So an LLM as a judge framework where they use an LLM to judge another response from LLM. And this LLM that they used was a RAG model where the corpus was this medical textbooks, medical guidelines, and like stat pulse, all the documents. So this RAG as a judge took each reasoning trace, checked their corpus, and then used an LLM to understand, give a score of plus or minus in the sense that are these answers right or wrong, right? It was later also validated by a subset of it, they also validated by the experts, right? And this, so what is happening? So they use the RAG, so they generate these training traces, say, and they focus on MedQA, which is a medical question answering benchmark. And what for each training, for each question answer, they had these reasoning traces like step one, step two, step three. And for each step, they had a score associated with it, right? Say if it is Gemini, what score it had given, if it is Llama, what score it has given. Um, and finally, the answer they also had. So the training data set um, had plus plus minus is A and plus plus plus, and they went into the MetPRM. And so this training data was used to train Llama 3.1. And the idea is after training during inference, it would be able to generate the reasoning traces as well as a label corresponding to it, and then finally come up with the right answer. So they also have a reward model. So if you want to know in more detail, please go through the paper. It is very recent. It also has a very good code base and data sets given for it. AI agents. This is like a very new hot topic. So AI agents are made up of LLMs, right? Um, but the main difference is that in case you think of generative AI, um, you have a prompt and you give the prompt input and a text or an image or a song or some code, or you prompt it to write a code for you and it will generate a code for you. And that's the end of it, right? So so this is basically a reactive setup, whereas an agentic AI is a proactive setup where when you give it a prompt, it will perform the following steps. It will first understand what the prompt is about. It will then decide on a fixed number of steps, whereas here you give very clear instructions what the steps are. So you do not formulate any steps here. You write directly and it generates in one step. Here they decide or they plan what the next steps are. Then they execute the plan. Then that may be critiqued by another LLM. And in this way, the cycle continues in that. Generative AI is good for making creative content where the framework is you write something, a first draft, you use the AI to review it or to refine it, or you give specific directions that I think which is refine only that, okay, how do I improve it myself? What are the 5 points that I need to uh, improve, right? Whereas the agentic AI is a multi-step process. So if you think of um, the problem that, okay, um, I want to buy, please, you have a list of groceries to buy, and you asked this AI system to um, buy the grocery for you, right? So it is not a single step process, right? So why? Because it will involve breaking that problem into multiple steps. First, it will look at the grocery list and find the availability. So first it will find which are the grocery shops near you, right? That is near to your location. Second, it will have to go through it and see whether the grocery that you are looking for is available to it or not. Once it is available to you, third, it will has to look at the billing aspect of it, billing and the payment aspect of it. Fourth is the delivery of it, right? So it is not a simple step. It has multiple steps, and this workflow you have not directly defined in your prompt, right? So this is a multiple step process where it decides and plans. So if you go through this particular video, it will give you multiple examples. Like they give an example of a bank application where they use a combination of LLM agents. Um, some agents like LLMs can't be good at these interfaces, but it is bad at this business decision making, right? So, Virtual Lab is one such AI agent that was developed in the biomedical space. And the idea is to, they used different models. At first, it uses the protein language model ESM. It uses another protein folding model AlphaMore and a computational biology software. So in agents, it does not only have access to other LLMs, it have access to something called as tools like calculator. It can have access to Bing search, right? And nowadays it has access to browsers as well. Okay. And this virtual lab, they found that they were able to replicate or able to design 92 new nanobodies. Then this is another example where this is the example, or this is a more detailed understanding where each agent are defined with four criteria. One is the title, second is the expertise, third is the goal, and fourth is the role. And then they are done over multiple simulations and with some control. So the initiation is done by the human. Say the human researcher writes a discussion or an agenda for the meeting, and then onwards everything is taken care. So we have a PI who, and the PI is supervising the three immunologists, machine learning experts, computational biologist, and there's also a critique agent which critiques the ideas that are developed by the PI or the summaries that they have. Right? You can go into it in much more detail. So we have reached the 1 hour 30 minutes mark. Um, so I will try to quickly go over this part, maybe in 5-10 minutes, and let's see. Okay. So the evaluation setup is, as you can understand, that just these foundation models are tasked to do many things, but there are instances of leakages where these benchmark models are actually being used in the training data. Um, though, and that's why they are able to get good performances. To bypass that, and secondly, to replicate more real-world patient scenarios, Medhelm has been developed, which contains like 121 distinct tasks across different categories like clinical decision support, clinical note generation, patient communication and education, medical research assistance, administration, and workflow. And they have also 14 private data sets which they have not released, so that um, like LLMs do not perform any, are able to train on it, or there is no leakage of that data, right? And this kept in a benchmark fashion when we have a leaderboard, right? um, I will this is the will there in the slides. I will not cover it, it's more theoretical. um, but I will just maybe go over the findings. So in medical domain, more than accuracy, you need to have the following. First is external validation. So in case of an academic AI paper, by external validation, it means that you have to show that the performance improvement in your quantitative study also leads to clinical utility. For example, in summarization, if you have a 5% improved Rugel score, then you have to also show that these summaries generated by your model and that of the baseline model, when given to medical experts, they also see similar clinical utility in terms of say relevance, conciseness, faithfulness. So in our research papers, we have always add another section where we randomly select 100 summaries, and then give it to medical experts who then give scores in terms of a Likert scale, right? In our Parkinson's paper, it was much more stricter, where we had to show that the subtypes that we developed for the LRRK2 in Michael J. Fox Foundation LRRK2 model, because the population here was from Tunisia, was robust enough or also present in other populations. So we also tested on the MDS dataset and this population, which was from US and UK, and we only kept those subtypes which was sufficiently present in both settings and had sufficient matches in terms of clinical characteristics. Okay. We have to should move towards real world evaluation, because if your model just works on static benchmarks, and it may not be, it is highly likely it will not work in clinical deployment, and specifically in cases where there are high demographic shifts from the population. You need to perform this outcome action pairing, that before designing a machine learning model, you need to know, an AI model, you need to know, like, who is your stakeholder, who will use the model, how is it will use the model, what is the lead time that your model is giving, does it has a clinical utility to it or not, um, and yeah, so you have to perform the outcome action pairing first before you start with the model development. So this is was done by when LLMs was used to show that just prompting based in context learning based approaches work very well in case of medical summarization, and they also performed along with the quantitative evaluation, which used metrics like BERT, like Rugel, other metrics, and but they also performed the clinical reader study that used involving clinicians, and also performed safety analysis. So these last two stages are very, if not equally important, if you perform a AI medical, if you develop a medical AI model. So this continues that they were asked to um, um, evaluate in terms of some form of Likert scale in terms of completeness, correctness, and conciseness. So another important part that comes in when you're dealing with medical text or in general any sensitive domains is faithfulness. That is, does it introduces hallucinations. The hallucinations can be, if it is just not present in the source summary. It can be if it is factually incorrect. It can be something that it is ambiguous, right? So in this paper, in EML 2023, they show developed a contrasting learning-based approach where during summarization, they showed that such approaches were able to improve the faithfulness of the work. And they introduced multiple um, losses based on contrastive learning as well as with medical knowledge, and they combined it with the cross entropy loss, which was the standard loss, and they showed that these additional losses lead to better, more faithful summaries. uh, with interest of time, I will not go through them, and directly skip to the open questions. That is, still there is a lot of work that can be done. specifically in multilinguality, because most of these works are uh, mostly are done in the English language. So although there are multilingual models that have been developed, but its evaluation in case of the medical AI space is very slow or very lag. So there are very few studies. Um, Reliability of compound AI systems. So as these systems become larger and larger, it becomes more difficult to control, especially when these compound AI systems have come where now there are not single points of failure, but multiple points of failure. Like in case of RAG, now you have a retrieval system. So the point of failure can be because you retrieve wrongly, or you need to do re-ranking or other problems. Third, transparency, as we previously covered for the EU AI Act, transparency is one of the key pillars. So there will be a strong move towards not just simple explanations. There has been work that showed that when an AI or a LLM gives a response or chooses a particular options versus when it again asks to explain that option, it can be two independent steps. So there needs to be more integrated approaches to generating explanations. Fourth is, as you have seen with reasoning traces as and medical rationals, these are like long texts of multi-step complex reasoning, and this requires similar evaluation framework. So simple Rouge metrics are not enough to check whether two reasoning traces are similar or dissimilar. So there has to be a separate rational evaluation framework that has to be done both for understanding uh, what is a high good quality of reasoning trace, as well as good quality of a medical explanation, or in general explanations. Finally, clinician involvement. Currently, clinician involvement is still as a very nascent stage where we just give them summaries to evaluate. We may need to move towards a more integrated approach where it is not the model output, but they are somewhat involved more in the design stage, more involved in the deployment stage, and whether the AI conferences push more from the model development side to the adoption side, mainly in the medical space. Um, so the slides will be available to you, so you can go through them in more detail. Um, Saying this, I've just crossed the mark 1.5 hours. So saying this, thank you for listening. And if you have any questions, please feel free to reach out to me. And you can also go through my research articles, and I will be happy to talk more about them.